Hello, how's it going so far? Everybody having a good time this evening? All right. So today we're going to be talking about Agentic RAG. So before we jump into that, how many of us are familiar with vector search, the traditional RAG, so to speak? Raise your hands. Quite a few of us, that's good. But for those of us who aren't, it's about using some kind of a model to get a kind of an embedding of natural language that you can query more effectively for semantic similarity. But before we go into RAG itself, let's talk briefly about the motivations behind any sort of indexing, right? Because when you talk about retrieval systems, at the core of it, it's about how you store something and how you retrieve it. I mean, you could obviously push every single data point into one box and kind of sort through the entire entire box yourself every time you had to find something. But that wouldn't be very effective, of course, and that's why we use indexing of sorts. Let's go back to the basics. Suppose you have a shop that sells balls, right? 5 different colors. A guy comes every morning, he delivers 4 of them. And that's kind of your goal for a day, so to speak. You sell a total of 100 balls a day, 5 of each color. Somebody comes in, they ask for a yellow ball. You don't find it very difficult, because why would you? You've got only 4 of them. You look at the 20 balls, you pick the yellow ball, you sell it. Now, your business grows for a little bit, and now you have more demand. So suppose now you have different shades of balls. And these balls maybe are of different textures, different materials. Maybe some are rubber, maybe some are foam, maybe some are something else. So now you might want to sort them in some way. Suppose you place all the blue-colored balls, or shades of blue, so to speak, into one category, into one box, right? So now you have 5 boxes. 5 boxes filled with 5 different colors of balls. Suppose 2 years, 3 years later, now you're selling about 50,000 balls a day. Now you cannot possibly sort through maybe 10,000 balls to find out which one's rubber and which one's foam and which one's something else, maybe cork, right? So now you want to index even differently. So my point here is indexing in any manner is not just once you index and that's it. It's oftentimes not that. It's a spectrum. How much you want to index and how much it will benefit you when you're trying to query, which is to retrieve a certain ball in this case. When the sample size is 10, you can pick out very easily. You may not need indexing in the first place. Whereas when the sample size is 50,000, you might need 2 different indexes, so to speak, to find the right balls. Now, let's think about the paradigm, right? The paradigm is when we are indexing, we are taking some sort of an unstructured data, and you're putting it in a structured format so that you can find it easier, right? So think of SQL. So what does SQL do? SQL is used for querying on relational data. Now, what is relational data? You could technically store every single data point as a natural language string, but we go through the effort of finding what those natural language strings would indicate for each feature. Maybe you have a feature called, or column called color. Maybe you have a column called size. Maybe you have a column called material, so to speak. And you take the time, when you put the data in there, to indicate what that particular row indicates. So that you specify the color, you specify the size, you specify the material, so to speak, right? So at query time, when you write an SQL statement and you execute it, it's so much easier to find the right row or the right rows than if you had to sort through every single one of them, right? There's also this focus about insertion and query. It's always that balance that when you're inserting, if you do more work, if you take more time to insert at insertion time, at query time, you can reap the benefits of that structuring to get the results much faster than otherwise. Why is this important? Well, this is the heart of any retrieval system. That how much do you index versus how fast can you get the right data back at query time. Now, in coding, of course, you see indexing in many different ways. You have Python dictionaries, which are like key-value pairs, so to speak. It's very fast, of course. You're storing everything in memory, so to speak, and you kind of get a one-shot O of 1 retrieval. On the other hand, you have SQL. You kind of pick out the right features, you log the features accordingly, and at query time, it's very fast. You don't have to sort through every single one. You can just look up those features. In vector search, you have something called a hierarchical navigable small world. Now, vectors in the end are just numbers. It's an array of numbers, maybe say 300-dimensional vector, right? So 300 numbers clubbed together, that's a vector. Now, when we do cosine search, if you have, say, 30 vectors or even 300 vectors, you may not need an indexing, right? So you can potentially loop through every single one of those vectors. When a user queries the system with a new natural language prompt, it might just loop through the 300 vectors, look at the cosine distances, and pick the minimum, right? It's a for loop. But when you scale that up to maybe 3 million vectors, that becomes less and less effective. So what we do is we use an indexing here as well. We use this index called the hierarchical navigable small world, which is it's a hierarchical method of indexing vectors, that which vectors are more likely to be together. So it's an approximate nearest neighbor algorithm that most of the vector stores use, including our InterSystems vector store as well. So let's now dive a little deeper into Agentic RAG. So one of the ways that Agentic RAG can be effective is called deep research. So I'll talk about 3 of them. We'll talk about 3 different use cases, what Agentic RAG could be. And my goal here is to kind of make you think about how can we use agentic systems to make indexing better and to make retrieval better. So when you go to ChatGPT, for instance, most of the agentic work that we see on a platform like ChatGPT is unindexed. So deep research, for instance, what it does is when you ask it a question, it will go through a web page. It will find, say, links that might be relevant based on the text, based on the website, so to speak. And it can jump. It can do multi-hop. So it will look at a link. It will go in depth into that web page. It will read through the stuff. It will go through another web page. Usually, it's on the internet at least, you want to have a hard set limit of how many times you want to hop. If you hop too many times, now suddenly you're 10,000 pages deep and your user is waiting for 10 minutes or maybe even an hour before they get a response. You don't want that. So you want to optimize the query time to a certain extent. How do you optimize query time? By limiting the number of hops in a completely unindexed system like deep research on ChatGPT. So again, what are the nuances of deep research? It's query time processing. So it's not query optimized. The entire processing is happening at query time, right? So when you start a deep research, oftentimes you'll see it'll take you 6 or 10 minutes to get you the result or the report, so to speak, from the deep research. So it's not indexed. There's no indexing, which is a good thing, because we don't want it to index our own personal data, because it's a system that lives on the internet. But it works on dynamic data. So the thing about indexing is, sometimes, if you choose to index, there's overhead to it. So you're doing work before by expecting to not have to do a lot of work at query time, right? So what happens when the data changes? In my previous example, when we talked about the different types of balls, right? So we had few different colors. Now, when you discover that these balls come in cork or rubber or maybe foam, now you have an index of all the balls sorted by color, right? Right now. So you have a box full of blue balls, red balls, yellow balls. Now you have to take all the balls from each and every box and re-index them according to their foam or cork or so on and so forth. What I'm getting at is that when you index some data in a certain way, when a new feature is involved, you might have to re-index the entire data all over again. Now, this is obviously a hassle, right? So if you do not index at all, you can completely not worry about a changing data set. No matter how dynamic the data is, which is the case with websites, when you go on the internet, the data is constantly changing. You wouldn't want an indexed system most of the times, right? There is some form of indexing involved, of course, like Google did that for a long time, like this personal page rank and all sorts of things that you want to have an index on. But for open-ended deep research, you may not want an indexed system, at least on the website. But not every application of Agentic RAG is open-ended research on the internet, right? So a lot of it can be on proprietary data that does not change a whole lot. Can you also do open-ended exploration of that? I will show an example of that as well. Let's talk about query-focused RAG. Now, how does it differ from regular RAG? Well, it's simple. You take a user's query, you understand what kind of data the user is looking for. If I say, hey, give me the top 10 movies from 1980 to 1985, right? If you put that into a RAG pipeline, right? Imagine you have a data set of maybe 10,000 movies from IMDb with ratings. It has to go through the entire data set to figure out which movies were the top rated between those years. But you have to provide that entire context to ChatGPT. There's two concerns here. The first concern is that that context may be way too long. Imagine if you have 10,000 rows of movies, you may not be able to fit all of that information into the context that ChatGPT provides. Second concern is, because you're giving it so much data, even if you had unlimited context, because you're giving it so much data from 1960 to maybe 2010, it has to understand which rows correspond to 1980 to 1988, or so to speak, and then kind of use the LLM-powered inference to figure out the result. The core idea behind any type of AI engineering is that you want to confuse the LLM the least possible. So you want to take out all redundant data, and you want to give the LLM only the data that it needs to work with. Query-focused RAG is much of that. So in my example of movies, you would figure out that there's a range. So a start date of 1980, end date of 1988. It will do a SQL query, maybe on the database, saying that the date field should be greater than 1980, should be less than 1988. It executes the query on the database, gets a new table. Now this new table may be 200 rows long. Instead of 10,000 rows, now you have 200 rows. If you don't even need to give all the 200 rows to the LLM. You can sort it by maybe the ranking. You can give the top 10 directly from SQL itself, and you can provide the names. That these are the data that we gathered from the SQL database. Now tell me what are the top 10. Now, instead of processing 10,000 rows, it's processing 10 rows. And that 10 rows exactly has the answers it needs to give you. So that is kind of the idea behind query-focused RAG. Figure out from the user's query what is relevant, filter the database, and give me the results. Next. Now, this is what I call deep index. It is like deep research, really, but with the indexing involved. The idea is this. In deep research, you're doing open-ended research on the internet. But imagine you have a corpus of a few documents, maybe 10 documents, maybe 10,000 documents. And all of them have references. If you ever read research papers, as I'm sure some of you do, you would imagine they would have references to other research papers. They would say that maybe X et al. Wrote about this particular algorithm. How do you look at that? Well, towards the very end, you'll find it. But now that you find the research paper, you usually go to Archive or Google and search it up. You look at that research paper, and then you kind of hop through research papers. Now, imagine if you had all the 10,000 research papers in hand, you could index every single one of them. You could have a sense of the topic itself, that this concept is referred to there. So you could have an LLM jump through research paper to research paper and kind of have a broader sense of individual algorithms, individual concepts, and things like that. So it's like deep research, really, but you're indexing on top of that. The benefit? You're not waiting 10 minutes to get your results. You're waiting a few microseconds because it's already indexed. It already has a good sense of what those concepts mean. I will show an example of this as well. Now, with that said, let me go back to my laptop and show some demos on what I've been working on. So this is DeepIndex, right? So this is a book that I had ChatGPT write me. So this is called Echoes of the Skyward Archipelago. So it's a sci-fi novel, essentially. It has a bunch of pages, and it has references. Like the research papers, for this demonstration purposes, it's only 10 pages long, really, but it has references for pages. So you can see a pallid sun rises over the skyward archipelago, see page 2. And page 2 would have some stuff written about skyward archipelago, right? Now, if you did a deep research on this corpus, if you asked it what is skyward archipelago, the idea is it would go to page 1, it would find the term, and it would see the reference, see page 2. It would go to page 2, it would see what it's talking about. If there's no more references related to skyward archipelago on page 2, it'll stop there. And maybe it will go through some other pages in one glance, but maybe it won't. And then it'll get you the result at the very end. So it's happening at query time. Deep research happens at query time. So it will have to do the jumping through the different pages at query time. However, deep index is different. So my idea was, when you click on index, now this is, why is it so fast? Well, I've done it myself. It takes about 3 minutes. I wanted to spare you the time. So I created the index and stored it as a Parquet file. In this instance, I'm loading it directly from the Parquet file and displaying on the screen. So for instance, if you go to Skyward Archipelago, you can see the summary. So what it did was, it browsed through every single page, it figured out the references, where to look for, and when a line is found about Skyward Archipelago, the next line is parsed, and it sees that if the next line references this previous line. If it does, it keeps it in context. If not, then it kind of moves on before it finds that term directly again. Like so, it generates this piece of text. These are sentences directly concatenated from the main corpus across the several pages that we've seen. It also notes the sources where it comes from. Now what I've done is, I've summarized whatever we gathered over there, omitting the references and such unimportant details, and saved the summary itself for this particular concept, which is Skyward Archipelago. I've mentioned the sources over here, so you can click on the sources. Page 1 talks about it, page 2 talks about it, and probably page 8 also talks about it. And I've done that, and this summary is done with a focus on the query. So it's a query-focused summarization on Skyward Archipelago. So it's not a generic summary. And it's doing that same thing for the different terms it finds. It does the same thing for refraction market, Atlas Nexus, so on and so forth. Now, if you vectorize these summaries, the next time a user asks the system what happened in Skyward Archipelago, or maybe what happened in Nexus, Atlas Nexus, these summaries would be the only ones that are most relevant to that search. Instead of getting 8 different sentences from 8 different pages, which mention Skyward Archipelago, and you would have to kind of parse through all these different sentences, concatenate, and then reason on that. Now you're reasoning on the first summary, which has all the important information included. So this is what I call deep index. So you're indexing multi-hop and storing the index as a summary, storing that as a vector in your vector store. If it's big enough, you can use HNSW indexing on top of that to make the vector indices also fast to query. And then when at query time, it's very fast. At deep research would take 6 minutes for something where this one would do it in less than probably 5 seconds. The second one that I wanted to show was smart filtering. So here is also a dummy data set that I generated using ChatGPT. So it has a few names. It has dates when certain activities were performed. And these activities are also generated by ChatGPT, mostly focused on sci-fi. So imagine a query of this nature. What did Echo do between May 1 and June 30? Now, if I submit this, let's see what happens. Now, it gives us some results. So this is the smart search, so query-focused RAG, right? So what happened in the back end of this system was that it figured out that I'm talking about a date range, May 1st to June 30. I prompted it in a way that it makes certain assumptions, like assume that the year is 2025, because that's what the dates have mostly in the data set. And such assumptions are actually very important when you're designing production-grade AI systems, because if you don't use those assumptions, these systems can be fairly fragile at certain cases. So you want to use like your own personal knowledge, subject matter expertise, to have those assumptions baked into the prompt itself for the use case. So what it did was, it went through the query, it picked out the dates, it picked out the name. So it's not only the dates, but also there's a name component to it. And it filtered the given data set, which had 20 columns, 0 through 19, over Darius, Lux, and Echo. And it figured out the few columns, the few rows that pertain to Echo and within the date ranges. It figured out the activities as well. So given this data, it is generating a response that directly answers my question. So this is an example of what query-focused RAG looks like. You're picking out the important details from the user's query, you're making the query on the database, you're getting some response back, and based on that response, generating some answer. The deep research part I already talked about earlier. I would not go into more detail with this, but it's similar to deep index, except it is not doing any indexing. It is really just, at query time, it's going to do the multi-hop retrieval of the content. So that was most of my talk, actually. Thank you so much.